So for our next talk, we have Michał, who's from Nethermind, and he is going to present a new zkSNARK that has the smallest communication cost of all updatable zkSNARKs. So very excited for this talk. Thank you for being here, and take it away.
Thanks a lot. It's a joint work with Helger Lipma and Jano Sim from Simula. So, as introduced, I would like to talk about Vampire, and Vampire is the most communication efficient zkSNARK with updatable setup. But more, I would like to talk about how zkSNARKs are built, like virtually any zkSNARKs we have, how they are built. What are the building blocks, and how choosing particular building blocks affect, well, various things. So what are the trade-offs? What trade-offs are available for us to have the snark of the properties we desire? Okay, so Vampire. So let me start with this. So our zkSNARK needs only 4 group elements and 2 field elements to show that a statement is true, and this is regardless the size of the statement. So this is really nice improvement over the past schemes. So to put you into context, for example, PLONK needs 7 group elements and 7 field elements, and it's like more than, so the proof is more than twice as big. Then we have Marlin, which needs like 13 group elements, Sonic, which even needs like 20 group elements. Of course, we also have Graph 16 zkSNARK that needs only 3 group elements, but well, Graph 16 has known limitations, like it's non-updatable. So it means that if you are given a SRS or CRS, then you cannot just allow people to update it to ensure that they feel secure with that particular SRS. An SRS that is generated needs to stay and cannot be changed. And Graph 16 is also non-universal. That means that you need to have a separate SRS for every circuit you want to show. On the other hand, Vampire, similarly to PLONK, Marlin, Sonic, is updatable and universal. That means that you can generate a single SRS and have it for every circuit you like, up to some given size. Okay, so how this was possible? So it was possible because of 3 things. So first of all, we used R1CS light arithmetic representation instead of R1CS. And that allowed us to shave like 2 group elements versus PLONK, or even 3 groups elements versus Marlin. We introduced a novel sum check argument called count, what allowed us to shave like 1 group element versus Aurora sum check, which is, for example, used, for example, in Marlin. And we also used more efficient way of batching polynomial commitments. Okay, so how zkSNARKs are built? So we have, as usual, we have prover and verifier and some relation. And the prover wants to convince the verifier that for some x, it knows witness w such that they are in this predefined relation. So to that end, I'm going to present an idealized model, which is not very efficient, but from this idealized model, we know how to compile things to an efficient zkSNARK. So to convince the verifier, the prover sends some polynomials, some bunch of polynomials, P11x, P12x. Then the verifier sends a random challenge. The prover responds with another set of polynomials, and it goes back and forth, okay? Eventually, the verifier sends, I would say, like a special challenge, evaluation challenge, and the prover responds with evaluations of these polynomials at this special challenge. Then the verifier checks whether some equality on the evaluations of the polynomials hold, and we are done. Yeah, as I mentioned, this is idealized model, which is not communication efficient because, like, for the sole reason that the sending polynomials is really not efficient at all. Okay, so our first step was going from R1CS to R1CS Lite. So let me introduce R1CS Lite. So similarly to R1CS, we have an arithmetic circuit with multiplication and addition gates. And this circuit is described in some matrix W. And we have also a vector Z. So the vector Z is built out of 3 subvectors, ZL, ZR, and the vector ZL dot ZR, which is pointwise multiplication between ZL and ZR. And ZL can be interpreted as a vector of left inputs to the gates, and ZR right inputs to the gates. And what we want to show is that WZ equals 0. And this is very similar to R1CS, where we don't have a single matrix, but we have 3. And we have matrices ABC. A corresponds to left inputs, B corresponds to right inputs, and C corresponds to the outputs of multiplication gates. And what we want to have is that A times Z times B times Z minus C times Z equals 0. So we also have vectors ZA, ZB, ZC, which are multiplications of A times Z, B times Z, C times Z. And eventually, what we send in this proof are 4 vectors, is vector Z along with this vector ZA, ZB, ZC. Okay, on the other hand, in R1CS, we have a single matrix, which is bigger than matrix in R1CS. And we show like a single, that a single multiplication is 0. And eventually, what we need to send is only 1 vector. So that allows us to shape the communication of 3 group elements. Okay, so we had this picture about how SNARKs are built. So actually, we can update it and replace this first message to a polynomial Z, and also evaluation at Z. Okay, so let me briefly discuss how we go from matrices to polynomials. So we have a matrix W and some vector Z, and we want to have a product of them to be 0. So, but you know how the multiplication of matrices works. So what we require is that we have for all x in some age, this sum of y in age of wxy times zy be 0. Okay. Oh, I didn't mention one thing. So this matrix we don't numerate rows and columns by like numbers like 1 to up to say n, but we use some multiplicative subgroup h and elements of that multiplicative subgroup to numerate them. That's why we have x in h. Okay, so we can define a polynomial such that for every x, this polynomial takes this value we need to show it 0. We can go even further and introduce polynomials that interpolate elements of the matrix and elements of the vector. Finally, doing some mathematical trickery allows us to introduce like a single polynomial that has this property that we don't need to to say like what happens for every x in H, but we can have like just, you know, one polynomial. Okay, so the next step is count, our novel sum-check argument. So in sum-check argument, we have two parties, prover and verifier, and prover. And here I'm not going to talk about zero knowledge, so I gave them the same input, namely the prover and verifier knows polynomial x, some value v, and the group H. So H is this multiplicative subgroup of size n, and what prover tries to show to the verifier is that if it evaluates the polynomial p on every element of this group, and it sums all these evaluations, then the result will be v. And sum-check argument is basically an argument for that to be true. And one of the most used sum-check arguments is from Aurora. So before we continue, let me introduce polynomial z, which is a zeroing polynomial. I just realized that everybody should probably know what z at x is, because that was one of the questions required in this submission form for this conference. And Aurora uses the following fact, that if the sum over h of p evaluates to v, then there exist polynomials r and q such that px equals v by the size of h plus x times rx plus qx zx. So what actually prover does in this setup is it sends the value v, rx and qx. And then the verifier just checks whether this equation holds. Okay, so that allows us to continue with our considerations on polynomials. So we see in this picture, we have this polynomial p, and now we introduce a new polynomial, phi xw. So we introduce the second variable just to make rid of sum for a moment. But then we also fix the first coefficient. Okay, so we pick some random alpha and we introduce psi alpha at y, which has x equals alpha. And then we have a nice sum over y, psi alpha y equals 0. So what we actually do, we compute r and q such that phi alpha x equals x times rx plus qx zx. So we come to this picture where we replace the second set of polynomials sent by the prover by the sum-check argument. Good. So now let me go into count. So before I go to count, I would like to say something about KZG commitment scheme, which you probably know. So in KZG commitment scheme, we need a trusted setup, SRS. It's a number of group elements, g to the s, up to g to the sk, where k is the biggest degree which a polynomial we commit to can take, and some element h in the second group. So we have our polynomial f, and the commitment is just evaluation of this polynomial at this secret point s, represented as a group element. And the assumption we have now is that it's infeasible to compute g to s to n if this n is not in this range from 1 to k. Okay? I think this is the security assumption that is for most zkSNARK used. And now we have a very simple observation that if we want to have a polynomial, if you want to commit to a polynomial that has non-zero coefficient fm, so the coefficient next to x to m, then the SRS needs to have g to the sm, right? Because otherwise this assumption would be broken. So now into count. So we modify a bit our trusted setup and we introduce a gap. So our trusted setup is now GGS, g to the gap minus 1, g to the gap plus 1, up to g to the 2 gap. So basically the adversary, the prover, cannot commit to polynomials that has non-zero coefficient next to x to the gap. And we use the following fact, that if f of x is of degree smaller than size of the h, then sum over elements of h is equal to f at 0 times size of the h. And we call it v. As mentioned, so let's assume that the degree of f is smaller than a gap minus 1. And we introduce another polynomial, f prime x. It's equal fx times x gap minus v by h x gap. And it doesn't look very nice, but let me say a bit more about it. So let's look at this particular polynomial. So it starts with x gap, right? Because we moved everything by x gap. And then on the first coefficient, we have f0 minus v by h, x gap. So for the prover to be able to commit to such polynomial, we need to have this value to zero each other. Okay, so how count works. So we have prover and verifier. The prover now knows the polynomial. The verifier knows only the commitment to the polynomial. The prover computes this polynomial f prime and sends commitment to f prime. Now the verifier needs only check that this f prime was computed correctly. What is done using bilinear pairings. Okay, so we had this picture using Aurora. So now we can shave additional group element, additional polynomial, by replacing the Aurora sum check with count. And more precisely, as I mentioned, this is idealized picture, right? So we don't actually send polynomials because it's like super inefficient. What we really do is we send commitments to polynomials. Okay, so we have like one step remaining, is the most efficient batching. Or maybe it's not the most efficient batching, but it's a batching with a different trade-off, I would say. So let's have evaluation points x from x1 up to xk, and some polynomials f from f1 to fm. And let's use dist a to say like what's the number of distinct elements in a vector. So we have two ways of batching polynomial commitments. So first of all, for each I, we can batch openings of all polynomials fj evaluated at xi. So to put it like more illustratively, we can batch, say we have like the polynomials f1, f2, f3, and we can batch all of the openings that open at some point x1, okay? So it doesn't matter which polynomial we are opening, it only matters that we open at the same point. So this needs to send, here we need to send like dist x openings. On the other hand, we can do things other way around. So for edge j, we can batch openings of all evaluations of fj. And here the thing is that, so we have all these polynomials f1, f2, f3, and we can batch all the openings of f1, all the openings of f2, all the openings of f3, regardless of number of points they are opened at. And in this case, we need to send like these f openings. Okay, so this is a trade-off. When you need to open your polynomials at multiple points, then you want to use the second way of batching. But if you have like multiple polynomials evaluated at the same point, then you should be fine with this first way of batching. Okay, so currently we are investigating various variants of vampire. One of them is a transparent vampire. So we ask the question, why do we need SRS in our zkSNARK? So actually we have two things that require SRS. One is the KZG polynomial commitment scheme. But instead, we could use like some Frye-based polynomial commitment, right? Like in STARKs. On the other hand, we have count, which also relies on SRS. But instead of count, we could use Aurora. So we would be worse by one group element, but we could also remove SRS. Altogether, that would give us a transparent vampire. So other variants and trade-offs. So we have this trusted setup versus trustless. So trusted setup allows us for a more efficient verification and shorter proofs, but also that allows us to use count, which also makes the proof shorter, and it's as a sum check, it's a more efficient argument. On the other hand, we could use transparent SNARK, which would blow up our proof size to logarithmic, but the SRS, that would be, the proof size would be logarithmic, the verification would be also more difficult, and we would need to use Aurora. We have also like a third variant, where we use trusted setup, but instead of count, we just use Aurora, and that allows us to have a shortened SRS, an SRS which is a bit more MPC friendly, and we can utilize existing SRSs. Because when we use count, we need an SRS with this gap, and like most of the SRSs you see in the space don't have this gap. So and that concludes my talk. If you want to learn more details, check our paper. It's on ePrint, and I'm happy to take questions.
Awesome. So we have a mic. So if anyone has any questions, I'll bring you the mic. Any questions? Oh, one question here in the back.
Hello, I'm Dmitry Kovratovich. Do you have any kind of concrete efficiency benchmarks for your scheme and something like comparable settings?
Yeah, we are working on the implementation. So the thing is that I think that the biggest trade-offs we have in this setting come from, sorry, let me go back. This R1CS versus R1CS Lite. So here, the thing is that we need to evaluate bigger matrices, right? Because we have this blow up from n times n to 3n times 3n, and that makes the prover a bit less efficient. However, count is more efficient than Aurora, because, well, it's a super simple sum check arguments. So, well, I don't have any numbers right now, but we are working on implementation.
Any other questions from the audience? Okay.